Thank you for your interest in InSync Tesla, the real-time adaptive traffic control solution that you can deploy in just one day. When Rhythm Engineering was designing this new product enhancement, as well as this presentation, we gave ourselves three challenges. The first challenge was, how can we build a product that delivers benefits to the motorists, pedestrians, the community, and the deploying agency, which far exceeds the capabilities of any other ITS or adaptive traffic control solution? Meaning, how can we create the most value for our deployment partners? Secondly, how can we ensure that our deployment partners can deploy it in just one day? Meaning, how can we accelerate the delivery of these benefits, and how can we minimize the expense of deployment so that all communities can have the benefit of this product? And finally, how can we show you these benefits in such a way that you'll have confidence that this product, that InSync Tesla, will work in your community and for your agency? So here's how we're going to do that in this presentation. First, we're going to take a minute and understand why Rhythm Engineering builds InSync and InSync Tesla. Why do we do what we do? Secondly, you're going to have the opportunity to witness a deployment from scratch of InSync Tesla. We're going to take a couple minutes and learn how InSync works, what are the adaptive algorithms, the model, as well as the hardware pieces that drive the system. We're going to take a look at actual field results from across the country of InSync deployments. We're going to hear from our deployment partners, traffic professionals like yourself, that have chosen and deployed InSync and get their experiences on both InSync as well as working with Rhythm Engineering. And at the end, we'll take a look at pricing and next steps for InSync Tesla. We said we would start with why. Why does Rhythm Engineering do what it does? Well, it begins here with the extremely high cost of traffic congestion. In the United States alone, $115 billion are wasted in time and fuel sitting at red signals. That's the equivalent of $731 for every motorist on the roadway. That's essentially the tax we pay for traffic congestion. That's too expensive, that number's too high, and we're confident we can bring that number down. But it's not only a monetary cost. There's a public health and environmental cost as well. Every year, vehicles on the roadways spit out over 80 billion pounds of pollution and emissions into our atmosphere. This makes our cities dirty and ugly. This has an environmental cost, and it has a public health cost. It makes our children sick. But this is the most important number. Every single year in the United States alone, 30,000 people die in traffic accidents, which isn't to mention the property damage only accidents and the severe injury accidents, which number in the hundreds of thousands. We know this number is too high, and we know we can bring this number down. Thousands of these accidents occur at signalized intersections, and InSync has been proven to drive down the incidence of crashes at signalized intersections and on corridors. So that's why we exist. Rhythm Engineering is here to empower traffic professionals with innovative and affordable tools to help them deliver loved ones to their destinations faster and safer. InSync Tesla is the next of those tools. Historically, InSync has been available in a couple different detection configurations. The first was using our proprietary IP Ethernet-based cameras. Those cameras allowed us to see and measure traffic as well as give visibility to the corridor to traffic professionals. A couple years later, we came out with InSync Fusion. InSync Fusion leveraged the existing physics-based detection present on the corridor and at intersections along with our cameras, giving it very robust, very accurate detection information. Well, InSync Tesla is the next detection configuration for the InSync system. It empowers you to leverage your existing or preferred forms of detection plus all of the benefits of InSync. So it is now InSync real-time adaptive traffic control using only your preferred detection, which may be inductive loops, it might be third-party cameras or video detection, it could be radar, magnetometers, or microwave, or any combination of those on your corridor, while also receiving the full benefit of the InSync system. Now let's take a minute and hear from our founder and CEO, Dr. Reggie Chandra, as well as get a little background information on the deployment we're about to witness.
We're making history here today. Normally it takes about 2 to 3 months for a timing plan to be deployed out in the field. So, and adaptive traffic signal control takes about 5 to 6 months. The reason we are making history today is that we are going to be deploying adaptive in a day. What we're going to do today is that we're going to go up to each of the traffic signal cabinets, install the equipment, and then turn the adaptive on. So right now it's about 8:30 in the morning. By the PM peak, about 3, 4 o'clock, adaptive should be on and operational.
Yeah, we're outside of Woods Chapel and Independence Avenue at the first intersection, and it's going to be a stretch of 5 intersections and 4 cabinets, with the centerpiece being the I-470 interchange, and that'll be the middle of the corridor, and it stretches about a mile down the road. So the major goal of this InSync Tesla deployment is to progress traffic in the AM to the interchange and up the ramps, and in the PM to progress traffic away from the interchange, and the commuters can get to the residential areas.
We've been working on this project for over a year, trying to simplify InSync to make it more user-friendly. And then I was on vacation with my family, and somewhere along that time when you're wrapping up, ready to come home, all of a sudden an idea came. Why don't we have an adaptive that we can turn on in a day? No one's tried it before. So that's where it came up. I highly recommend people take a lot of vacations.
Some of the challenges that may happen today are if the cabinets aren't wired completely as we've been told. There are some challenges, and we may have to make some adjustments within our software to fix that. So that could take some time, but if it is all as advertised and as they've told us, then it should go very smoothly, and there should be no issue finishing it in a day.
Now that we've given you a little preview of the deployment project for the day, I want to give some context to this corridor. It is the Woods Chapel Road corridor in Lee Summit, Missouri, which is a suburb of Kansas City, Missouri. If you're familiar with InSync deployments, the name Lee Summit might ring a bell. We do have 3 other corridors in Lee Summit, but none of them are intersecting with this corridor here. As you can see, it's a fairly typical interchange type corridor. We have other characteristics are the emergency vehicle preemption along the corridor. It is a route to schools, and maybe most importantly is the ongoing residential and commercial development along the corridor. If we look at the adjacent land uses, we see the residential areas at the west side. Towards the center, we have the retail and commercial area. And again, most importantly, is this area reserved for future development. That's what made this corridor particularly good use for adaptive traffic control, and specifically InSync Tesla. It's because the agency knows that there's a good chance that traffic volumes and patterns are going to change in just the next few months or next couple years as this land continues to get developed. So adaptive traffic control and InSync Tesla in particular makes good sense here, so that the agency doesn't have to continue to retime and make adjustments based upon new traffic conditions. The adaptive traffic control solution can take care of that for them. Some of the other challenges on the corridor are just your typical daily traffic variation that we'd see on most corridors. Congestion from freeway incidents. Obviously, an incident on the freeway slows down rates of travel on the freeway. People choose to use the surface street. That can lead to intense spikes in volume. And then there is a nearby recreational lake off kind of the west end of the picture that you're looking at, and they have special events that to some degree are unpredictable changes in traffic patterns that are a good use for InSync Tesla as well. As we're going and witnessing this from scratch deployment of InSync Tesla, I want to give you an idea of the order that we're going in as far as the order of installation. So we saw the guys out at the first intersection here on the west end, and obviously they'll move to the east to the second intersection. They'll skip over and do the last intersection, or I should say the third intersection at the far east end, and then come back and do the ramps. So now let's head back out to the corridor and hear a little bit more about why this corridor is a good fit for InSync Tesla, and watch them wrap up the first intersection.
Some of the interesting thing about this particular corridor, and one of the reasons we chose it, is the variety of physical detection mechanisms they have in the field already. We have video detection, we have inductive loops, and a radar detection system. So the InSync Tesla system is able to work with all of those seamlessly.
Today we have 2 engineers working on it and 2 of our deployment technicians that'll be installing it, and then we'll have 1 additional guy that'll be observing it remotely, making sure everything's working properly. So a total of 5 people working on this.
Prior to today, the 2 agencies that we were working with, MoDOT and Lease Summit, have installed wireless networking systems to allow the communication to occur across the corridor, and they also installed some panamorphic cameras that allow us to view what's going on and will allow them to view their corridor from back in their offices. Also, the Rhythm personnel were preparing the processors, setting up networking, IP addresses, those sorts of things, but there really wasn't a whole lot of additional work necessary to hook things up. We'll just wait until we got into the field and plug things together, and it should be good to go.
Kevin,
you guys got these all screwed down?
Kevin has my zip tie. Fine for you.
You got it in detector mode?
Lease Summit just arrived here to help us put the system into detector mode. Detector mode to us means all the inputs are coming into our system, but then we're just translating right into the controller again to use their timing plans that are already on the controller. The next step after this is to free up the controller and put it into adaptive mode, but we need to do this prior to that step. Lease Summit is letting us bring in all the calls into our system, and then we pass those directly on to their controller.
Probably temporarily take the recalls out so we can validate that our system can place calls to the controller. Okay. And then and then we'll validate that we get all the status information, all the loops information, or all the camera detection information.
Now, are you going to need...
So this is one of the things that we said might happen today. The wiring here is non-standard. Fortunately, we can make those adjustments within our software, but we need to know what the pin mappings are. So we're going to get one of the technicians from Lease Summit to tell us exactly what those pin mappings are, and then we can make those changes in our software and go from there.
Go to sleep.
All right, so we finally got our first intersection done, and we're done. Intersection's up, running in detector mode, and we're going to move on to the next intersection.
Now that we've kicked off the project on the corridor, let's take a second and step back and discuss what is InSync. What are the model and the concepts and the algorithms that underlie the adaptive performance of InSync?
My name is Reggie Chandra, and I'm the founder of Rhythm Engineering. My career started as a traffic engineer for the city of Springfield, my first job out of school. Undergrad in civil engineering, master's in traffic engineering from University of Florida. Since that time, we're talking 1993. Since that time, when I was working with the city of Springfield, till now, all I've done is optimize synchronized traffic signals. The number one phone call I used to get when I was in the public sector was this: why am I waiting on the side street when there is nobody on the main street? And I will try to explain. It's because there is a hold on the main street once the side streets are gapped out. Now, you know as well as I do that the motorist doesn't care about the limitation of our hardware. To them, they're just wasting time and gas, polluting the air, waiting on the side street when there is nobody on the main street. The second phone call I used to get was this: it skipped me. I waited on the left turn for 15 minutes. And you would say, oh, signal is in transition. Here also the motorist didn't care what transition was. All they experienced was that they got skipped and they waited on the left turn. The analog architecture of the traffic signals is the culprit for these phone calls. The latest and greatest controllers that we have right now are what I call as electromechanical controller emulators. They are solid state, digital on the outside, but on the inside, all they're doing is emulate an electromechanical controller. The essential components are the dial that turns around once so often, which we call as a cycle length. Then the dial has spins in it that trigger relays that gives you the split, the green splits. Then you have one fixed point in the dial that you can reference an offset to. Let's look at the modern controllers. They are solid state. Some of them are capable of running 120 timing plans, except if you were to run any more than 5, 6 timing plans, you go into what I call as transition hell, which is the signal just goes into chaos when it's switching from one plan to another. The moment you say dial or cycle length, split, force off, or yield point or one fixed point where offset is a reference, the moment you say these 3 things, all you're doing is you're emulating an electromechanical controller. In 2005, we formed Rhythm Engineering, and in 2008, our solution InSync was rolled out. Here are the 3 components of the InSync model. One is we convert the analog controller operations to digital. And then the second one is we have a local optimizer that looks at the intersection and optimizes the intersection. And then we have a global optimizer that looks at the entire intersection network. Let me talk about the first module, which is convert analog controller operations to digital. As a solution to this analog sequential architecture is that we have a plugin that makes the analog architecture into a digital state machine. Now, what is a state machine? This concept has been around for decades, more than 50, 60 years. The metaphor is this: an analog system is like your old TV, where if you wanted to go from channel 7 to channel 10, you have clicked your way through. Now, in a state machine, which is a modern remote, if you wanted to go channel 1012, you just punch in the number and it goes instantly to that. There's no linear sequential movement. Here is how we digitize the traffic signals. A state in a state machine is defined as a pair of concurrent phases. Any 2 phases that can exist without conflict. For instance, on the top left, I have the northbound left turn and the southbound left turn. That is a state. In a digital architecture, I can call it a name. Here I'm going to call it A1. And any time I want to bring up A1, I can do that. If I want northbound through and southbound through, state F1, if I wanted that, I can call it. And it's going to show up just like punching the buttons on your remote on a TV. So you have 8 states, which are the phase pairs, and 16 sequences. You can have less. Like for instance, if you say that in your city you don't want to have lagging left turns, for example, the sequence E goes away. Sequence B goes away, sequence D goes away. And the state machine has to pick from any one of those depending on actual demand out in the field. No common cycle length, no transition, no wasting green time by dwelling on the Main Street green. You serve the traffic purely based on demand. Let's look at the local optimizer. So in our system, we have a camera that is facing every approach. And these cameras determine the queue length at every lane. As cars approach in, it recognizes the cars, and we keep a running count of how many cars are waiting at the intersection. Now, the way we do that is that we draw detection zone along the contour of the lane as far as the eye can see. And then we subdivide those detection zones into segments, which are approximately the length of a car. And we count the number of segments, and therefore we get the number of cars that are waiting. Imagine a person standing at the intersection. He's got tokens that he's required to hand out to each car as it approaches the intersection. And he's also required to give the tokens if a car waits 5 seconds. The car on the left turn, it pulled up, gets a token, waits 5 seconds, gets another token, waits another 5 seconds, gets another token. So as you can see, as cars approach in the video, the token count increases for each lane. This person that is handing out these tokens, he's greedy. He does not want to hand out tokens. So what he does, or what this algorithm does, is changes the lights to minimize the number of tokens given out. We are optimizing for the number of cars that are waiting and the duration of their wait. So a quantity, which is volume, and delay, which is the time it has been waiting. And changing the lights to make traffic flow efficiently. The algorithms in InSync and InSync Tesla are the same. The only difference is in the way in which we determine the queue at the stop bar. Both models are equally effective. So that is the local optimizer. What we do in the global optimizer is that we create speed lines throughout the corridor. On the bottom you have speed line 1, the green line, which is northbound direction. The orange lines are the southbound direction. I'm assuming that it's uniform speed. In reality, speed changes between segments. What we do is over time, we generate speed lines. So if you are a car and you're traveling at speed and you're close to the speed line, you're going to get all the way through. At each signal, the InSync's global optimizer serves the coordinated movement to progress platoons of vehicle through the time tunnel. Then InSync turns control over to the local optimizer to intelligently serve the best phase combination or phase pair and green times based on real-time actual traffic demand. Here is the entire model. If you had the power to turn your coordinated movements green when you wanted them to be green, and rest of the time the signal ran intelligent actuated, that is the model. We appreciate your interest in the InSync model. For more information on InSync and studies of its benefits to communities, please visit our website. Thank you.
Now that we've heard more about how InSync's adaptive algorithms, concepts, and models work, the next question is, but does it really work in the real world? InSync has the benefit of being the most broadly deployed adaptive traffic control solution on the market. We're deployed and trusted by more agencies than any other adaptive traffic control solution available. What that means to you is we have this broad range of experience already built into the product, whether it be varying weather climates, road geometries, agency objectives and philosophies, even motorist expectations, as well as existing hardware and central system softwares that we integrate with. The experience of all of those is already built into our system to your benefit. If we look at it from a numerical perspective, almost 2 million vehicles roll through InSync intersections every single day. That's because we've been selected for use at almost 700 intersections at 109 corridors in 58 cities and 19 states as of April 2012. Now let's take a minute or two and look at InSync's performance on these corridors. Before we get into the specific MOEs at each of these corridors that chose to do a before and after study, we want to point out what was being done before InSync to attempt to coordinate and manage traffic flow. As you'll see here on the screen, most of these corridors were already running coordinated time-of-day plans. So when you look at these before and after benefits of InSync, keep in mind that these are above and beyond coordinated time-of-day plans in almost every case. It's also important to note that most of these studies were done by independent third-party engineering firms commissioned by the agencies themselves. We actually make available to you on our website all of the studies themselves so you can download them and look at them in detail, as well as the contact information for each of these agencies so you can interact with them directly and ask them questions if you choose. So now let's look at some of the MOEs of the benefits of InSync. Now let's take a look at the findings of those studies that were conducted. The first MOE we look at here is delay reduction, reducing the amount of time vehicles sit and wait at red signals. What you see across the country is anywhere from almost 50% to almost 90% of delay is reduced with the deployment of InSync, again above and beyond their existing coordinated time-of-day plans. The next MOE we'll take a look at is stop reductions, reducing the number of times vehicles stop at red signals along the corridor. We see reductions of 33% on the East Coast in one of our most saturated corridors, all the way up to actually 100% in one case, and people usually scratch their head when they see that 100% number. That simply means when they were doing the after runs in their floating car method study, they simply did not stop on the corridor. More importantly, I hope you see on this slide, is the consistently high level, 70, 80, 90% stop reductions, again, above and beyond their existing coordinated time-of-day plans. The next MOE we'll look at is travel time reduction, the amount of time it takes a vehicle to travel from one end of the corridor to the next. Again, very high, consistent numbers across the country in this case, from 20% in one instance all the way up to 50% in the Bay Area in California. And if you think about it this way, what that means is if that corridor took beforehand 8 minutes to travel from one end to the next, and you're a motorist that drives that corridor twice a day, you've now given back each one of those motorists 8 minutes into their life. And what we usually hear from folks is, you know, I get to hit the snooze bar one more time, or I get home earlier to my kids at the end of the day, or I get to put in a few extra minutes at work if that's what they choose to do. But if you take those savings and multiply them by the tens of thousands of motorists that travel that corridor each and every day, the benefit to the community is of course very substantial. The next MOE we'll look at is reducing the consumption of fuel on these corridors. Here we see reductions in fuel consumption by the vehicles on the corridors anywhere from 16% all the way up to 38%. That has a great environmental impact as we're consuming and burning less fossil fuel, but also an important economic impact as we're keeping money in people's pockets as opposed to in their gas tanks and flowing out their exhaust pipes. Now, as you can imagine, with less fuel consumed, we have fewer emissions. We see emissions reductions anywhere from 23% all the way up to 42%. Again, an important environmental impact as well as a public health impact as well. If we monetize these benefits on just an annualized basis, we begin to see returns to taxpayers like this. Millions of dollars being returned to taxpayers from the deployment of InSync. Now, of course, if you multiply that out times the many years that InSync will be in place and running, the benefits grow that much larger. We typically see benefit to cost ratios in these independent studies that I've been talking about anywhere from 30 to 1 up to 50 to 1. Depending on various conditions. So we're returning to taxpayers a substantial amount of value for what is a relatively low investment and quick investment in InSync. But the most important numbers that we have to show are these. This is InSync's ability to reduce crashes on corridors. This is our ability to save lives, save injury, and save property damage accidents. So now we would like to show you some of the feedback from the deployment partners of ours from across the country. We think the numbers are very important and hold a lot of weight, but we also want to make available to you the actual experiences of the deployment partners that have selected InSync and deployed them in their communities.
The InSync system is performing great. We have gotten results back from 2 of our corridors, and the numbers look great. The travel time and the number of stops has improved dramatically. So it has met our expectations.
Does it work? That's the first question everybody asks. The application we use it in, it works great.
It's performing great. As far as expectations, we have initial before and after studies that show our travel times are in the 30% reduction range. Our speeds are up 30-35%. Stops are down, over 50%.
It's working. It's doing a real good job with it too.
It works exactly like I expected. If you say, does it work better? No, because I expected that I was going to get all green lights, and that's what it's doing.
The improvements that we saw were far and beyond what we expected. We reduced the travel times through the corridor by anywhere from 40% to 70%.
Traffic's moving in all directions. It's optimizing as it's supposed to.
The input from our staff and from our time into the system is very little, very minimal.
Yeah, we feel that the ease of installation, the ease of maintenance, and the benefits you get from the improved traffic flow is just remarkable in my eyes.
We have received a lot of positive feedback from our residents. They, especially people who are on the side streets, have noticed that they do not wait as much. They're able to get through the intersections much easier. We have also seen a dramatic improvement in the travel time on the corridor itself.
Basically what we're saying is we're getting pretty much the side streets clearing real well. We're also handling Main Street traffic well.
We got rave reviews from not only the public officials, but as well as from the motorists.
The response from the public and city leaders has been very well received, real supportive. If you drive the corridor, you see a change.
There's a whole lot less congestion today than what we typically see. And that's the goal for the whole corridor, is to reduce congestion, much more so than we can do with traditional traffic timing plans.
Traffic engineers know how difficult it is just to squeak another 5 or 10% out of a signal, out of its capacity of a signal, just doing very minor things that they can do with timing and those sorts of things. So when you see these types of gains, the numbers will speak for themselves.
In one time frame, it's dropped almost, it's in the 90%, the amount of stops that have dropped. And that's just phenomenal. Usually you're looking at 15%, 20% is great numbers, but having them up to the 90s, that's just, I'm impressed.
I know the travel times were up to 8 minutes before, and I think we've got them down to 3 or 4 minutes.
Just like it advertised, drive the entire corridor on green lights.
InSync works and has made a huge difference.
It's working well for us.
It worked well, just day one.
If you're considering an adaptive control system, that the Rhythm system is the best on the market.
InSync works. It made a huge improvement.
So for the last few minutes, we've been showing you information on InSync. Let's take a couple minutes to talk about specifically the enhancement to InSync Tesla. I'd like to point out before we get into the exact components and architecture of the system that all products from Rhythm Engineering, including InSync and InSync Tesla, are invented, designed, assembled, configured, and supported directly by Rhythm Engineering. It's not a distributor relationship. It's not a licensing relationship. The folks who wrote the code and assembled the boxes that are shipped to you are here in our offices and simply a phone call away. That means we can offer very powerful, very fast, and very accurate direct support to our deployment partners. And what you'll typically hear when you talk to our existing deployment department partners is that they buy InSync in the first place because of its powerful benefits, the ones that you just saw a minute ago, but they come back and buy from us again and again because of our level of support and our focus on partnering with agencies, not selling and shipping boxes and then disappearing. It's also important to note that when you're investing your taxpayer funds, you are investing them back into a 100% American company. Now let's get into the architecture of the system. So as we discussed briefly at the beginning of the presentation, InSync Tesla can take in inputs from any form of detection. We're 100% compatible with all detection devices, be it loops, radars, video, magnetometers, microwave, etc. Those detection inputs are fed into the InSync processor, which is the state machine you heard Dr. Chandra talk about earlier. That's where the intelligence resides. The InSync processor makes the decision based upon actual real-time traffic conditions, what is the best state or concurrent phase pair to serve at that signal. It then feeds that information into the existing controller in the existing cabinet as a pair of concurrently permissible detector calls. What this means is InSync Tesla is an overlay system. It works with all of your existing hardware, all of your existing detection. We work with every major make, model, and type of controller, whether they be 170s, 2070s, NEMA TS1s, NEMA TS2s, your NEMA cabinets, your 330 cabinets, all the central system software products on the market. We are 100% compatible with all of them. There's nothing to throw away, nothing to discard, and of course that's one of the reasons why it can be deployed so rapidly. So as we mentioned, InSync Tesla can work with every major common form of detection and any combination of those. So if you have multiple forms of detection at one intersection or along one corridor, that's perfectly fine as well. And of course, multiple different types of controllers or brands of controllers or even types of cabinets along a corridor, we can be compatible with all of those as well. So there's nothing to change, nothing to upgrade, nothing to throw out. Continuing on the architecture of InSync Tesla, we do need interconnect communications between each intersection. We have about half of our deployments are running on simply Ethernet over copper, meaning on a twisted pair of copper, which of course means that fiber or wireless are plenty sufficient for InSync and InSync Tesla's needs. We do make available a panamorphic camera like the view that you see here if you do not have monitoring at your intersection. So when we talk about prices at the end of this presentation, if you do not have monitoring, video monitoring at your intersections, typically like with something like a PTZ, we make available to you and included in the price this monitoring camera, which allows the agency as well as Rhythm Engineering to view the intersections and support them remotely, as well as keep an eye on traffic conditions. If we normalize the view of that panamorphic camera, we see it broken out into per approach views like what you see here. Now that we've looked at an overview of the hardware components and the architecture of InSync Tesla, let's answer the question, how does InSync Tesla determine demand and optimize service at each intersection and along the entire corridor? It starts with stop bar detection for each phase. Ideally, we'd have stop bar detection specified for each lane, but if you've tied together lanes of the same movement, that's perfectly fine as well. InSync Tesla takes in that information from the stop bar detection and uses its intelligence to learn the prevailing volumes for each phase by time of day and day of week, and of course is always learning so it can relearn as necessary. It uses that information to schedule the green times, phasing, sequences, and coordinated movements based on the prevailing traffic conditions. But it is not married to that schedule. As changes occur, as there are variations in traffic volumes and patterns, it adjusts immediately during the same phase and during the same sequence to real-time demand. So while it schedules based upon what it's learned, it also can immediately make adjustments inside the same phase and inside the sequence to real-time changes in demand. So let's take a look at a graphical depiction of what we mean by this. Let's say InSync Tesla has decided for a particular time of day and particular day of week that this is the best sequence to serve based upon what it's learned about traffic conditions at that intersection. It begins to serve the first movement, the southbound through and the northbound through, and recognizes heavy demand on the northbound through movement. And again, here's where the intelligence starts kicking in. It says, okay, well, I'm going to serve that northbound through movement in the next phase as well. So let's give that first phase pair 27 seconds of green time and move on to the second phase pair. When serving that phase pair, it now recognizes it also sees particularly high demand on the northbound left movement. Again, it understands that it's going to serve that movement in the next phase pair, so it can serve the appropriate amount of green time and move on to the next phase pair. But here it does something very interesting. It says, well, now I've seen heavy demand on the northbound through and the northbound left. I'm going to go ahead and schedule to reserve those movements inside this same sequence. It then serves the opposing lefts, 19 seconds of time. It checks to make sure that there actually is presence at this northbound left and the northbound through, and it serves them another 15 seconds of green time. So now it's learned at this time of day, this day of week, it tends to see particularly high demand on the northbound through and the northbound left. So when it schedules the sequence for the next time that this time of day and day of week occur, it's going to now lead with the northbound left and the northbound through. I should have mentioned that all of these, let's assume all of these lefts are protected lefts. It makes the illustration work a little bit better. This northbound left and northbound through, and it serves them the appropriate amount of green time to clear out those queues, and then moves on to the next phase pair, which is the southbound through and the southbound left. In doing so, this time around, it notices there's particularly high demand on the southbound through. Again, it understands that it's going to serve that movement in the next phase pair, so it serves the appropriate amount of green time and moves on to that last phase pair and serves it the appropriate amount of green time. So now the system is relearning again. At this time of day, this day of week, I saw particularly high demand on the northbound through one time, on the northbound left, and on the southbound through. It then comes up with this sequence. Again, protected lefts in this case. It's going to start by serving the southbound through and the northbound through the appropriate amount of green time to clear those queues. It then moves on to the opposing lefts, and this time it receives particularly low demand on the northbound left movement. It serves that phase pair the appropriate amount of green time, but also goes ahead and cancels the next phase, which included that northbound left and the northbound through that it's already served because of the low demand recognized on that northbound left movement. It finishes serving that phase and moves on to the last phase pair in the sequence and serves it the appropriate amount of time. So I hope this illustration shows how the InSync Tesla intelligence is learning the prevailing traffic conditions by time of day and day of week, but also able to immediately make adjustments in both in all the green times, the phasing, and the sequencing at each individual intersection based upon real-time actual demand. It does not have to wait to the next cycle or wait for 5 minutes later or download a new timing plan in order to make adjustments. It makes adjustments immediately based upon actual demand. And that's what we mean when we say real-time adaptive traffic control. It's not only understanding demand in real time, but it's making adjustments and adapting in real time. Now that we've taken a look at the hardware components, the architecture, and the intelligence of InSync Tesla, let's head back out to the corridor where you'll hear a little bit more description about it in an in-field setting.
Well, here we are at the second intersection. The crew's working on installing the components. The basic pieces that go into the cabinet are the InSync processor itself, the physical wires from the controller into our system, and then additionally a equipment panel that has the power supply and the networking connections, a switch that allows us to hook up the pieces that use the network.
This is InSync Tesla. This is our InSync processor. It's this rectangular shaped white box here. That is actually the InSync processor that is installed with all the InSync products. And that's basically all there is to the installation for the hardware of InSync Tesla.
One of the benefits of InSync is that it is compatible with all types of controllers and cabinets. Now, InSync Tesla goes even further. It is compatible with all types of cabinets, controllers, and all types of detection system. In this corridor that we are turning on today, we have two intersections with video, one with induction loops and the other with radar. So it's a combination of detection devices, and InSync Tesla is 100% compatible.
Along this corridor, we're using a wireless network to connect the systems. Really, it doesn't matter which networking technology, whether using fiber optics or wireless networks, or even just simple twisted pair copper that's using an Ethernet extender to connect over that. The demands on the networks are very low with the InSync system, so we really are able to operate with any kind of a network connection.
And also what we have is that in the last release of InSync, even if the communication goes down, your arterial will not suffer any loss. It'll function even without interconnection between signals.
Now that we got a little bit more information from the corridor and heard some more about the architecture and the components, let's ask the question, so what? So what that InSync Tesla is interoperable with all types of hardware and cabinets and central software and detectors. It can be deployed in a day. Well, the most important benefit is that you can make an immediate difference to your community. You don't have to wait years for traffic impact studies and data collection or building more lanes and considering new roadways. You can make an immediate difference to your community literally in a matter of a few days. Some of the other key benefits are the minimal acquisition costs. Because it installs so quickly with so few components, obviously the cost of installation is greatly reduced. You get to leverage your existing detectors. Those detectors that you've already invested in, that you prefer, you can take full advantage of those. There is no data to gather. There's not a laborious process prior to deployment of gathering field conditions and giving those to Rhythm Engineering or some consultant or something of that nature. So minimal time on the agency's part. There are no timing plans to build. Other solutions on the market that claim to be adaptive are really more like responsive systems that are choosing between various timing plans. With the InSync system, there are no timing plans for you to build. There's no intensive training required. We can typically train people in about a day or a day and a half on both the hardware as well as the user interface software for InSync. And again, nothing to discard. Those pieces of equipment that you've already made investments in, that you've already invested taxpayer dollars, you've been trained on, your technicians are familiar with, you continue to run those pieces in your cabinet. From an ongoing basis, you'll see that there's no net increase in management, and typically we see a decrease in the amount of hours it takes to manage those intersections and those corridors. Again, it's because it's the same hardware you already use. There are no timing plans to maintain, to be updated. Very robust failure mitigation mechanisms. If communications go down, if detectors fail, all of those types of things we have already thought through and put in robust mitigation strategies for. And again, the 24/7, 365 support directly from Rhythm Engineering. When you call Rhythm Engineering, we have the answer. We do not need to call overseas somewhere to get the answer to your question. We can solve your problem or answer your question immediately. So now let's head back out to the Woods Chapel Road and take a look at the guys completing the third intersection on that corridor.
So we're at the third intersection now. It's taken us roughly about half an hour per intersection. What we've done is split up into two teams. Kevin and I have been working ahead of the engineering team, prepping the hardware and the traffic cabinets.
The cable hub.
All right, so I'll screw this down last. So the most complicated thing we've run into so far has been just routing the cabling between the processor and the cable hub. And once we get that situation figured out, it really doesn't take much time at all. And then once you have it in place, making sure everything's secure and neat and tidy, that's the most time-consuming part of it.
Something interesting at this intersection at Lakewood Way is that we ran into our third different controller at our third intersection. So we can work with any amount of controllers on one corridor and work them together. This is the controller right here, and then right next to it is the MMU monitor.
Here at this third intersection, we're encountering our second type of detection mechanism. In this case, it's a radar system. They've got front and side firing radar for detecting the vehicles here. At the last intersection, we'll run into the third type, the inductive ground loop systems that will be operating the MoDOTs.
So we've just finished intersection 3 at Lakewood and Woods Chapel, and we're going to move on to intersection 4.
Okay, there we saw the quickening of the progress made by the crew in the field. Now I want to take a minute or two to give some context to the overall deployment timeline of InSync Tesla. It starts with the deployment partner placing an order with us, and we of course receive that order. The next few steps are we have some goal setting and kickoff meetings to make sure everybody's on the same page and seeking the same objectives on the corridor. We begin to procure and build and test the hardware specific to each intersection. Really the only thing on the deployment partner's plate at this time is just to verify the corridor communications are up and running and fully prepared. Over the next 30 days, we are creating an internal simulation of our configurations for that corridor. We ship the hardware. The hardware is delivered to the agency. Our folks come on site to do installation training and get everybody familiar with the hardware. This is a lot of what you're seeing in the videos from Woods Chapel Road. The controllers are freed up and the adaptive system is turned on. So what we mean when we say we can deploy adaptive traffic control in one day is this period of time. This period of time where we go from running whatever your previous coordination or signal timing methodologies are to being running in adaptive mode all happens within one day. And the majority of your time investment or your investment in hiring contractors all happens on this one day as well. After the adaptive system is turned on, we then go through some systems training with your team. And then from there, we're monitoring the system, make sure it's performing as expected. You'll hear a little bit about that towards the end of this presentation. And at that point, the project is complete. The InSync is deployed on the corridor, is up and running the way it should, and we go into what we consider support mode. We do check in on the corridor from time to time, and we're here to answer any questions you have or address any issues that may come up. Every project we sell comes with 2 years of unlimited both hardware warranty as well as remote technical support. Now let's head back out to Woods Chapel Road one last time to watch them wrap up the last intersection on the corridor.
This is our fourth and final intersection. It looks like 2 intersections, but it's really one 6-way intersection instead of a standard 4-way. This has gone real smoothly. We got this done in about 15 minutes. What we found is as we go along, we get in a rhythm and things go a lot more smoothly. What used to be a few hours is now just a few minutes with Insync Tesla.
The Insync Tesla model has been operating out in the field in different parts of the U.S. We've been testing it, we've been evaluating it, we have been calibrating it, and today it is ready to be released. Steve, you want to talk a little bit about testing?
There have been several places across the country where we've operated corridors now for 3-4 months that we've been running, and had success in all of those, and we're ready now to do this first deployment across the corridor from scratch.
And the beauty of the thing is that it's real time. It is looking at real-time demand every second and optimizing it. All intelligence resides locally. Communication failure, not a problem. In other words, it will happen. Things will break down, but Insync Tesla is designed to mitigate 99% of the issues that happen at traffic signals. Insync Tesla is the personification of one of the values of rhythm engineering. We want to make a difference to the motorists. We want to bring loved ones safer and quicker to their destination. So if we can provide tools to the traffic engineer where they can plug in a device, configure it, and move traffic the way they want it, we've achieved our goals.
This has all been built on work that we've and research we've been doing over the last several years, and like you said, it's the same basic model, but we've continued to evolve it to where we can work with all kinds of equipment.
The name Insync Tesla, we wanted to honor one of the greatest inventors of our time, Nikola Tesla. Someone who dreamed up solutions, took mankind to places where they never went before, Nikola Tesla. So we decided to honor him with this version of Insync.
Yeah, really, this product is going to be hopefully as revolutionary as some of the things that Tesla did, where traffic professionals will be able to optimize corridors quickly and easily, where in the past they were afraid to do it because of the cost involved, because of the time involved, the project expenses, and we're making this to where it's so simple, so easy for them to do that there's no reason to not optimize all of the traffic corridors in a municipality, really making the drive home and the drive to work quick and simple and easy for everyone. Whenever you're doing an installation in the field, you're not sure exactly what you're going to run into, and had a few minor snags, but honestly nothing unusual. A few configuration issues where the cabinet detectors weren't wired up the way we expected, but it's pretty easy to deal with here, so things have gone well.
At our first Tesla deployment here, 4 intersections, we just wrapped up, and it is 4 hours on the dot.
1 year of development, half day of installation, and here's the adaptive turn on right here.
The next step in the process, after the equipment is in the field and the adaptive system is turned on, is to monitor it and make any tweaks or changes that are needed, which is done through our companion software, CentralSync.
Now that we're back at the office and have the intersections completely installed and operational, we can take a look at the graphical depiction of the intersections and what is currently happening at that intersection. As you can see on here, each orange indication is a current vehicle detection, and Additionally, you can see all the tunnels coming through and the progression coming through the intersection.
For the afternoon, they're going to watch the operation of the corridor, making sure that the initial parameters that we used for configuring the system match the reality of it. So we'll be tweaking the system if necessary, making minor adjustments to it, or verifying that all the phasing and such is set up correctly. But right now everything looks good, and we're just going to be watching it over the next few hours and through the rush hour peak to make sure that it's operating as we expect.
Our Central Sync software is a piece of software that we use here to set up our initial configurations for the systems. As you can see right here, each one of these nodes is representative of an intersection and an InSync processor inside the cabinet. On here we draw tunnel connections to associate the progression along the corridor in each direction. And with that, you can see it visually through this Google Maps interface, and then also you can visualize it through what we call our tunnel view. And in this depiction, you can see how the tunnels come through at each intersecting point, which represents an intersection. And each band here represents one of the coordinated tunnels. Additionally, within the Google Maps interface, you can change it to a satellite view to zoom in on an individual intersection and see the associated phases at that intersection. And you can pan across and see exactly what phases are at each intersection with each arrow. Also, you can set up the scheduler for the configurations throughout the day on this right portion down here, and that can be set up as one configuration to run all day or multiple configurations to run during the day. Once we're back from the initial deployment, we can use Central Sync to make any of the adjustments or tweaks that's needed for InSync.
Now that we've finished watching the in-field deployment of InSync Tesla, let's answer this final question. What is the investment required to get InSync Tesla up and running in your corridors in your community? If you're familiar with Rhythm Engineering, you know that we believe in very open and transparent and clear pricing. We don't want there to be any financial surprises in your project, so that you have a great experience and know exactly what's required. InSync Tesla is $25,000 per intersection. Now here you see the prices of the other detection configurations of InSync as well. I do want to point out that there is an additional charge for the intercept module, which is used to handle most commonly pedestrian intercepts, so that we can serve pedestrians along with vehicular traffic in an optimized and smooth flowing way. There is a project management fee associated with each deployment of InSync that typically runs about $1,000 or less per intersection. We do have pricing sheets available. Just simply request one from us and we'll get all this to you in writing. What we'd really like to do is to build a custom corridor analysis and quote for you, so you know exactly what the financial investment will be for your corridors in your community. I do want to say there are some other ancillary items that can be included, things such as in-cabinet monitors and keyboards, things like shipping and taxes and spare systems. So you'll definitely want to take those into consideration as well when doing your financial estimation, and that's the kind of thing that we would include in a customized quote. So to summarize InSync Tesla, InSync is chosen by more agencies than any other adaptive traffic control solution in the United States. It's a product that is fully validated by both our clients that you had the opportunity to hear from, as well as engineering studies, by and large independent engineering studies, and it's shown to make a dramatic improvement in traffic conditions even above and beyond the existing coordinated timing plans. That's because it's using real-time, local and global adaptive traffic control. It's compatible with all existing hardware and detectors, so your controllers, your cabinets, and your detectors. It's 100% compatible with all of those, as well as your central software systems. And it's very powerful. It's even patented technology. And finally, very competitive pricing, as you just saw, very comparable to standard detection systems. There is no active operation of the system. You're not going to need to increase your staff or your manpower. You should actually see a decrease in the amount of operation labor associated with your InSync Tesla corridors. There are no timing plans to build or maintain, and that substantial ROI that we saw earlier in the presentation, the benefits you're bringing back to your community every single year from your deployment of InSync Tesla. So we thank you again for your interest in InSync Tesla and InSync. We encourage you to take a look at our website for more information, or of course contact us. We can do that custom quote and corridor analysis that I spoke about a minute ago. We can let you know exactly what the financial investment will be to have InSync Tesla on your corridors, and take a look at your corridors and see how well InSync Tesla is a fit for them and what type of benefits we think we can deliver.